The last type of response we're going to look at is our critically damped response. And so the total response for this case is shown below. And so remember, this is sort of like our Goldilocks porridge. This is sort of the sweet spot between too fast and an overshoot and too slow but not overshooting. So our critically damped is the fastest possible response that we can have without overshooting. And remember, it is just one single point that's sort of the division between overdamped and underdamped. So in practice, we can design for critically damped, but if we have slight changes in our parameters of our system due to noise or some unforeseen sort of parameter, then we could sort of slip from critically damped to either underdamped or overdamped. So let's look at an example system. So g of s equal to 9 divided by s squared plus 6s plus 9 is going to give us a critically damped response. And so again, note, the only thing we're changing are the parameters of this system. So we've just been changing this a value this whole time. Just like with all the other cases, we can find our poles. In this case, we have s plus 3 squared. So we have s plus 3 times s plus 3. So what we have are two real and repeated poles. So two real repeated poles. So this is going to correspond to our critically damped case. And let's go ahead and draw this in our S-plane. So we have our real axis and our imaginary axis. And in this case, both poles are going to be at -3. You can either put the x's sort of almost right on top of each other, or sometimes, I believe in the book, they'll draw it a little bit below and to the right. As long as you're clear with how you do that notation, that's all right with me. So that's what it looks like in our S-plane. We have the two poles at the same spot, and both of them are real. Our natural response, so again, drawn above is the total response. The form of our natural response is as follows. So overall, it's pretty similar to what we saw for our underdamped case. So we have C of t is equal to K1, which is just some constant, e to the minus alpha 1 times t, plus K2 times t, e to the minus alpha 1 times t, where this alpha 1 is, of course, the location of our repeated pole, and the main difference, or rather the only difference, between this natural response and that of our our overdamped response is we have a t in one of these two terms. So those are all of our response types. What we're going to do in later videos is come up with a better way to sort of generalize our second order systems so that we can easily discuss certain parameters and know what response type we have and more easily find characteristics of our response.